Hi, I'm Ryan Voltz, and on behalf of myself and my colleagues, today I'm going to be talking about the development and status of Zephyr, a distributed MIMO meteor radar network for space weather research. This is part of the 2020 virtual CEDAR Workshop, and I'll start with some background information that will be familiar to a lot of CEDAR scientists, because we care about the mesosphere and lower thermosphere region, or MLT region, but it is hard to measure because in situ measurement is often impractical. It is too high for aircraft and balloons, but too low for spacecraft, so really our only options are rockets, which are expensive and infrequent. Remote sensing, which does exist, is unfortunately very sparse. It doesn't have great coverage temporally or spatially. And the neutral atmosphere is particularly difficult to measure, but of course it's coupled with the ionosphere, and so we do care what the neutrals are doing. We all know that the frontier is system science. Whole atmosphere modeling of the entire atmosphere and ionosphere requires a system view, but models need more constraining data in order to provide a comprehensive view. We do know that coupling from the lower atmosphere through the MLT to the ionosphere is strongly influential on the ionosphere. The energy contribution is comparable to input from above from the magnetosphere, but the full wave spectrum is unknown, and temporal and spatial dynamics are poorly sampled, so what we badly need is more data. This is in contrast with scientists studying the troposphere who have the NEXRAD weather radar network, which provides continuous coverage in space and time of the troposphere and enables weather modeling and prediction to a much better level than what we can manage with our sparse data sets of the upper atmosphere. So this DAISY project, Zephyr, our goal is to develop and build a distributed MIMO meteor radar network for observing MLT winds that can support future large-scale deployment and address some of these data sparsity issues and progress CEDAR science in the system-level view. The Zephyr Meteor Radar Network is a joint project between MIT Haystack, where I am the PI, and the University of Colorado Boulder, where Scott Palo is the PI. We have heritage from an NSF MRI award that built the prototype Simone network in Germany, which was initiated by our collaborators on this project, Juha Viernen and Koki Chow. And the network that we're building specifically for this DAISY project is located near CU Boulder and covers the Rocky Mountain region. So I'm going to go over a few different objectives of this project. The first is to optimize system design and produce a remote deployable integrated receiver unit. But first, before I really talk about the system design, I have to talk about the techniques involved. So meteors happen all the time from sporadic micrometeoroids entering our atmosphere, and we can scatter off of them with HF radio waves like a mirror in the typical specular scattering case. And when we receive that scatter reflection, it can have some Doppler shifts imparted on it by trail movement with the wind in the upper atmosphere. And so by measuring the Doppler shift, we can also infer wind speeds in the upper atmosphere. We can also look at the diffusion rate of the meteor trail, which is a function of signal-to-noise ratio, and that can relate back to temperature in the upper atmosphere. So we have two physical parameters that we can measure with meteor radar. Typical meteor radars are monostatic with a pulsed waveform, and they use an interferometric receive array to calculate direction of arrival so they know where the scattering point is located in space. They also typically give a wind averaged over the field of view of the entire meteor radar, so you have one wind sample as a function of altitude and time per particular meteor radar installation. Now, what the new technique we're using is a coded CW MIMO meteor radar, where the coded CW technique uses transmitters that transmit continuously with independent pseudo-random codes. And then you can have receivers that decode those signals from multiple transmitters with little interference between transmitters because of the pseudo-random coding. And with that, you get a combinatorial number of links all over just one frequency. So you can have a transmitter surrounded by multiple receivers and other transmitters, where each receiver can see multiple transmitters and decode all those transmitted waveforms separately and make separate independent measurements. And so you can imagine a kind of scaling out like a network in this case, where we're tiling it with transmit arrays and receivers. Some of the advantages of this technique are you get more detections from a variety of specular geometries. You get no range aliasing because we're using a continuous waveform and not pulsed. And you can get a non-degenerate wind field sampling, which is not possible with a single meteor radar. Now, beyond just the coded CW technique, which you might imagine as using independent single transmitters and then your typical receiver array to do direction of arrival estimation, we can advance to flipping that on its head and doing a transmit array where each transmit antenna transmits its own code, independent code, and you only have one receive antenna that can still decode all of those transmitted signals independently and do the interferometry on the receive side to figure out the direction that the transmitted wave took. And you can take that even one step further up to full MIMO, multi-input, multi-output, where you have transmit arrays and receive arrays, which both buys you increased signal-to-noise ratio and two independent estimates of the direction of arrival for this radio wave, so you can get independent estimates of the location of the meteor, which helps improve uncertainty of the measurements. So with Zephyr in particular, we're planning 2 transmit array sites. So we can step back to this diagram again. It's what this buys you, this MISO configuration or MIMO configuration, is flexibility in how you design your meteor radar network. So what we found often in early on deploying some of these SIMO systems is that it's expensive and hard to locate a transmitter, but it's also hard to locate a receiver array because you need more space. So often it's easier to put all the complexity in one site with a transmitter array, and then you can have simple single receivers that can be deployed much more easily and scattered in locations more easily. And so playing with those network geometries is one thing that's nice about this MIMO technique. And so with Zephyr, we've decided to, so far, go with planning to do 2 transmit array sites and surrounding those with 12 single receiver sites and then also 1 receiver array site so that we can test the MIMO capabilities. And over here is just a map of some notional locations in Colorado where we're thinking of putting some of these sites. The Platteville site is where we're planning our first transmit array site. Our roadmap is to iteratively build from a prototype design with the Simone system that we already have in Germany to support early testing and iterative design to improve on it. So we're starting with block 0, where that's basically the hardware and configurations that we already know how to do, getting out 1 transmit array site, or one transmit array site and 2 single antenna receiver sites, and starting on the software development. Then block 1 brings iterative improvements to the hardware and software, and we're just building out the network more, mostly with single antenna receive sites. And then block 2 is where we get into developing an integrated receiver unit, 2 of them actually, with a next-gen software-defined radio that can be fully autonomous and can be deployed to remote locations that are more off the grid. And for that, the software will require onboard FPGA processing to do the meteor detections, so that we don't have to transmit the full RF data. And so this is just an example of the rapid unit that Franklin developed at MIT Haystack, where it's a base with solar panels and an antenna attached, and then you can stick batteries and receiver units inside the base. And so this is what we're planning on deriving these integrated receiver units off of for block 2. And our current status with this Zephyr project is we're on this block 0 right now. We're in year 1, 6 months into the project, and we are currently procuring the hardware and starting to do some receiver testing right now, and hoping to have a full transmitter and receiver setup going by the end of the summer so that we can start collecting data and iterating on the design. Another objective of the Zephyr project is to create open source tools for radar operations, meteor detection and processing, and wind field estimation. So as I mentioned, this software development will involve not only the telemetry and control interface to control the radar and manage the data, but also algorithms to do meteor discrimination and detection to reduce the data, and wind processing to take the raw meteor data and output it into science products that the community can use directly. We strongly believe in the open source philosophy and that it builds community. So we're planning on making all this code open source, and we think that'll give us higher quality and easier maintainability because of many eyes on the problem. And we also know that a single entity can often create a bottleneck. If we want to grow this network and make it a large project with covering more than just the Rocky Mountain region, it's going to be hard to do that if one entity controls all the software. So having a community involved in the software development and making it open means that we can get better scalability in the long term. And it also encourages educational and amateur participation, and particularly with this project, it would be easy for students or amateurs to set up single receiver sites if they're within range of an existing transmitter and then contribute data back into the network. We're planning on basing all of our software on the digital RF data format that has been produced by MIT Haystack already. This is our format for storing raw RF data. So if we build everything on top of that, then it will be easy for people to process the data in new ways if they so choose. And part of that software development is doing the wind field estimation, and that's something that I'm in particularly giving a lot of thought to, because a meteor radar network gives enough information in order to estimate the 3D wind field as a function of time. And so what I'm working on is a new estimation algorithm using Gaussian process regression, where we model each directional wind component as a Gaussian process. Then you choose a prior mean and covariance for each of those UVW components, which then we can either fit those priors with parameters with some data, or apply physical knowledge if we have some, which we often do. And then once you have a prior, you can estimate the wind field from a set of Doppler measurements from the meteor radar, and from the posterior probability distribution, calculate the estimated winds. And you can do that at chosen points in space and time. It's not a gridded technique. And you also get uncertainties for the wind estimates included in the output. And so I like to think of Gaussian process regression as interpolation with error bars. And you can see in this simple 1D example, interpolating through these data points, that's exactly what you get. You have this mean of the posterior distribution and the variance with this gray background showing how much possible functions can vary between those measured points. And our final objective for the Zephyr project is to study the upper atmosphere in the Rocky Mountain region and measure the MLT wind field from a new mesoscale perspective. We obviously don't have any data yet, but I can talk about some of the data products that we're planning for the community to be able to use once this is up and running. Level 1, we just have our Doppler wind measurements directly and the meteor parameters. This is the output of the meteor detection algorithms. And then built on top of that, we have the wind field estimates that I've already mentioned. And we can also think about doing correlation and structure functions of the second order correlations between different points in this region. And I'll point to a paper by Juha Vierinen describing how to calculate horizontal structure functions using these MIMO meteor radars. And finally, level 3, built on top of those level 2 data products, we hope to put out information about horizontal divergence and vorticity, momentum and energy flux, and wave energy spectra. And so here's just an example of the wind field estimate outputs of what it might look like. We can see we can do slices in altitude and in time. So this is at 2 different altitudes, 88 and 92 kilometers, and this is 2 different times, 6 a.m. and 6:30 a.m. local time. We can see we can get a nice 3D estimate of the wind field that is much better than the single point averaged estimate of a traditional meteor radar. And so I'll remind you right at the end here what our long-term vision is we want continuous coverage in space and time of MLT winds. And so that means we want to build a radar network much like NexRad, but with meteor radars. And so that's the long-term vision, and I hope we'll get there. And so I'll leave up our contact information. If you have any questions, you can contact me at rvolts@mit.edu, or you can contact Scott at scott.palo@colorado.edu. Thanks for watching.